This month, we've come to the West Midlands and the magnificent University of Birmingham. The University of Birmingham gained its Royal Charter in 1900, and science has a long pedigree here. The university's first professor of physics, John Henry Poynting, measured the mass of the Earth in his laboratory way back in 1890. But we're not here for a history lesson. We're here to meet astronomers who are making great strides in discovering other worlds and going to the end of our world to do so. Welcome to the Sky at Night.
Unité, top.
And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Well, before we get to exoplanets, we've got to discuss the most exciting event to happen in astronomy this century, Christmas Day launch.
I know. I was there biting my nails. I mean, the launch of the James Webb Space Telescope. It's been delayed, it's run over budget, but it went up. But I was just terrified that something would go wrong. There were so many things to happen. But so far, so good. I mean, how do you feel about it?
Yeah, it's working brilliantly. The launch is always scary, but Ariane 5 took off on Christmas Day, lunchtime, very convenient for viewing. And we saw that last shot of James Webb disappearing to its orbit a million miles away, and that was good enough. But then the telescope had to unfurl, it had to click its mirrors into place, the cameras had to work. I think there were 330 things that could have gone wrong, and they all went absolutely perfectly. I think even NASA and ESA are a bit surprised that it's worked this well.
Yes, and I was told that it actually deployed, but they didn't get the feedback saying it had deployed. So there was a tense moment of, it hasn't deployed. And, oh, actually, no, it's there.
It's all fine. Yeah, everything works. So the telescope's now in orbit, and they've spent a few months calibrating the cameras. We've just got the first proper calibration image. So there's this beautiful star in the centre of the image, in focus from one camera at the centre of the image.
Unlike Hubble.
Yeah, that's right, exactly, which had those famous problems. But then in the background, there are these beautiful little galaxies that are just in the background, but they're there and we're seeing them. And this is an infrared telescope, so we can compare to the previous generation of infrared telescope. And if you look at the Spitzer image of the same field, all you see are blobs, and yet in this first not finished, half-calibrated JWST image, you've got a view of the distant cosmos. It's really exciting.
That's what high resolution. With that big mirror, you get the resolution, the detail.
Yeah.
It's going to be amazing what it does.
And so, to the main business of this month's programme, exoplanets. For most of human history, the only planets we knew about were those in our solar system. The idea that stars other than the Sun might have planets was, well, just an idea. But then, in 1992, we got the first convincing evidence for an extrasolar planet, and the floodgates opened. Today, our tally of exoplanets runs into the thousands. Amaury Trio has made a career of hunting exoplanets, and his recent research might mean that we'll be able to identify even more of them. Amaury, how are you?
Hi, Chris, how are you?
Yeah, I'm good, thanks. Congratulations to you and everyone else on 5,000 confirmed exoplanets, target we've just reached. How were most of those worlds found?
Most of these planets were found via the transit method. Transit method, conceptually, is fairly simple. You have a star, you have a planet, it passes in front of it and it gets a bit dimmer. So if you want to look at the light right there, you have your light, the planet passes in front of it, it gets dimmer. You see that the light dropped. It dropped for a certain duration of time, so it allows you to detect the planet, but also to measure its size. What's important is its size.
What are the disadvantages of using the transit method?
One of the main disadvantages is that you need to be exactly collimated, right? Your stars need to be in the same plane. If your planet here is passing in front of it, if it's here, orbiting, you don't see it.
From my point of view, I don't see a transit at all.
You don't see it, exactly. So you don't know, and only a small fraction of systems will show a transit.
So there is another method we can use, particularly if we care about a particular star, called the radial velocity method. How does that work?
So that method works by using Newton's law. So you know from Newton, if there's a force, there must be a reaction. So here, if the star attracts the planet must attract the star a little as well. So it happens that way. So imagine we have our star and our planet, and what will happen is that both will move around what we call a common center of mass. The star being heavier, it will move less. So you have both here that orbiting about one another around a single point. The star move a little less than the planet, which moves
So
a
it's
lot.
not the picture that we've animated on screen many times, which is that you have the star fixed and then the planet in orbit around the star.
Exactly.
Both are moving.
And what you will see from your line of sight is that you will see the star move back and forth.
As the star moves with respect to the observer here on Earth, there's a minute shift in wavelength, allowing astronomers like Amory to calculate the degree of the star's tiny wobble, and in turn, the mass of the planets responsible.
When we talk about the star wobbling like this, how accurate do our measurements have to be?
Yeah, they're very fine. So for instance, Jupiter about the Sun creates an amplitude for a signal of 10 meters per second. In order to detect smaller planets, our instruments now have a precision of about 1 meters per second, so that's walking speed, right? It's fascinating that we can measure such slight motion in a star.
So one system I know you've been looking at with both methods is Kepler-16, which is fascinating. Tell us about this world.
Yeah, it's a fantastic system because it has two stars instead of one at the center. So you have to think of, Tatooine, for instance, in Star Wars. What you have at the center is two stars of unequal masses. So there's a large one and a small one, and they orbit one another.
So this is what we call a binary star.
This is a binary star system. And around those two, if I can ask you to hold this two, right?
So I've got the two stars.
So then I'm going to put a planet. And there's a planet that goes about both of them at once.
Okay, not around one star, but
no,
about
it's
both
not
of them.
doing like this. It's not doing like, any. It's just going about both at once. What we thought would be interesting is to use the radial velocity method on these kind of stars in order to find them more efficiently, cheaper, and study their mass, study how big the systems are, etc.
So this means doing a targeted search, going to places where we know there are binary stars and staring at them.
That's exactly right. We see the motion of the binary, and on top we see a slight variation caused by the planet, with the idea that, that way we can study the system in greater details. And weirdly enough, because we know that our system is eclipsing already, it gives us a greater chance to eventually find them in transit, because it's hard to find the transit of a long period planet. You need to observe for a very long amount of time.
Yeah, so if I wanted to catch Jupiter transiting the Sun, I have to look
To wait
for
10 years.
best part of a decade, right?
Exactly. Actually, because you want to confirm it, you need to observe for at least 20 years. You need at least 3 passages.
Right. Okay, that sounds really, really smart and impressive. But first, you've got to find these planets.
That's right.
Have you? Kepler-16 was a case where we knew about it from transits, from space-based observations, followed up on the ground. Have you found any starting with ground-based observation yet?
Yeah, just about. You're arriving on a good day. So yes, indeed, Kepler-16, we wanted to show that our methods worked because people were a bit skeptical. We have to do a proof of concept. Now we've actually identified our first system in our survey. It's a system that actually had been previously identified as a second binary system also by the TESS satellite, by NASA. So you had the 2 stars, and then one of the planet that they saw was at a 95-day orbit. We were already observing, it was already in our sample, and we knew that binary was interesting.
So you had something to aim for.
So we had our data in, we thought, okay, let's confirm that 95-day planet. And lo and behold, what we detect is a planet at 220 days. So we detect another planet which had not been noticed in TESS, showing
Right.
the good point of our method, which is, radial velocity allows us to find planets at longer distances more easily than the transit method.
So the idea of finding more circumbinary planets from this radial velocity method is really exciting. What's next for the project? What are your ultimate goals?
We want to find an occurrence rate, so how often do planets exist around binary stars, because that's important to compare with the rate that we find around single stars.
Well, we should let you get back to work, but thank you for telling us about that latest discovery and for the excitement of circumbinary planets. It's
Right.
really good stuff.
Thank you, Chris.
Anne-Marie's high-precision observations require optimal conditions. But unfortunately, here on Earth, the perfect conditions for telescopes rarely mean perfect conditions for humans.
At the end of last year, Anne-Marie's PhD student, former physics teacher Georgina Dransfield, travelled to one of the most inhospitable places on Earth. Unless, that is, you're a penguin.
Oh my goodness, look at that waddle!
But even penguins would struggle to survive at her final destination.
So we appear to be moving towards a whiteout here.
So it sounds like a pretty tortuous journey to get to Antarctica and to get to the location. But what was it like when you got there?
Oh, it was magic. I actually have a video. It was magical to get there finally after all that traveling. So here you can see us, our Basler, when it actually just landed at Concordia.
And it's just gliding on the ice.
The Basler flight was, challenging, to say the least, not pressurized or heated. And then this through the window is when we first saw the base, which was amazing. When we got off the plane, I mean, we'd been in Antarctica already, and it had been like -10, but then suddenly we're struck by like -30. It was so violently cold.
And you want to get out of it?
Yeah, absolutely.
Actually, you do look well wrapped up there.
Yeah.
I can't imagine cold like that.
I mean, neither could I, obviously, because I thought that I'd imagined it and was prepared, and I absolutely was not. But yeah, actually arriving there and seeing the towers in person and then actually walking in there, it was really special.
So you work on a telescope called ASTEP. So what's it designed to do?
So ASTEP stands for the Antarctic Search for Transiting Exoplanets. So we're searching for exoplanets, planets outside the solar system, orbiting any star other than the sun, and we're looking for them using the transit method.
So that makes sense, but why Antarctica?
So it's actually not just anywhere in Antarctica, but this particular place is very, very special. We're at an altitude of about 3,300 meters. Wow. We're up on the Antarctic plateau, so we've got the altitude, but then we also have a really, really thin atmosphere because of the altitude, and the air is incredibly dry. So that means that also we have super stable conditions, and stars don't twinkle at us like they do at other telescopes. So this means that we get outstanding observing conditions at this particular site. And in fact, we get one night that goes on for a couple of months for uninterrupted observing. So that's pretty special.
Yeah. So what sort of work were you doing?
Well, there were 3 objectives for the mission. Firstly, we wanted to move the telescope from the old small dome to a new bigger dome that has kind of more remote control, so we can operate it more easily from Europe. And we also installed a new camera box with 2 cameras, one that can detect mostly red light and one that can detect mostly blue light. My main job was I developed and then went and installed and tested a new data analysis pipeline. So it's the software that takes us from what are basically photos of the sky to the end result that we want, which is the graph of the brightness of the target star that we're interested in over time, which is the light curve. So fortunately, we don't have to do all the work outside. We have there's shelters all around Concordia Station for the different types of science that happens. I actually have a video of the shelter.
So that's it?
Yeah, so this is the Astro Shelter. And so in here you can see, once we'd taken the telescope from the smaller dome, we brought it in here for reassembly and kind of rebuilding, also for testing the optical alignment in the new camera box. So all of that happens inside the Astro Shelter.
Okay, and it looks quite warm. People are just wearing sort of normal clothes in here.
Yeah, absolutely. Okay. Yeah, no, that's heated and you can be very comfortable in there.
So you do the setup within the sort of nice warm sort of a dome, but then you actually have to take the equipment outside. What was that like?
It was really challenging. So for the actual moving of the telescope from the Astro Shelter, where we did all the work on it, to the dome, there was a tractor and cranes. I have a video actually of this. So here you can see the equatorial mount is being lowered into the dome.
That looks scary.
Yeah, absolutely. I mean, big chains, big ropes, but it still feels precarious when you're watching it. So yeah, the really, really big, heavy stuff was done, and here you can see the telescope being moved into the dome as well. So this was a combination of tractor, crane, skidoo to get everything in there. But the camera box itself, he's just carrying it. He's walking down the steps carrying it, and there 2 of them are carrying it, and I was kind of walking behind, that way you walk kind of like just ready to catch something if it were to fall. But yeah, no, they were very safe and very careful with it. I mean, because this camera box is really the most expensive and most important part of this mission in order to make sure the mission succeeds. So yeah, fortunately, everything went well.
Yeah, so that's them sort of putting the covers on.
Yeah.
It's in place.
Yeah.
Phew.
Yeah, exactly.
So did you get first light? Did you actually get data coming through?
Yes, we did. So fortunately, there are a couple of stars in our field of view that are bright enough to be observed during daylight. Canopus is one of them. So we actually pointed the telescope at Canopus, and then we were able to kind of sit there and use the camera acquisition software, and we did see first light. I mean, we all just got so excited. It was really, really special to see the success of a mission that really had been, going for years and years. It was special to see it happen and to kind of share in that moment people who've dedicated their careers to this instrument and this project.
You were a physics teacher. You took time off to do your PhD and sort of get involved in research. And you've had this fantastic experience. Where do you lie now? What does your future hold? Back to teaching, or has this sort of given you the bug?
Ooh, that's a really tough question. I've absolutely fallen in love with research. The trip definitely, I mean, there's a lot of opportunities for travel to exciting places, to work on these telescopes, but I still miss teaching. There's something really special about kind of, teaching your students about a thing that you really, really love, yes. And then the ones that one day say, "Oh, miss, I think I'm going to do astro at uni," and that fills my heart.
And because of you.
Exactly, that absolutely fills my heart. So I mean, never say never, but for now I'm going to stay with the research.
Well, this truly was a trip of a lifetime. How are you going to remember it?
So now that you mention, I'm actually getting a new tattoo to commemorate the trip. So I'm quite excited.
So you've got quite a few tattoos.
Yeah, I've got a space-themed arm going on here. So I'm gonna, take one of the big chunks of space left and put a tattoo there to commemorate the trip to Antarctica.
Well, I think that's a lovely way to remember. And yeah, it sounds like a fantastic trip. And I think you've got to go again. And next time, take me.
I mean, if I can, definitely. It would be nice to have other English speakers there, among other things.
Well, thank you so much for sharing your story.
Oh, thank you for visiting.
For many of us, stargazing, the simple act of looking up at the night sky, provided an escape during the pandemic, and telescope sales are up as a result.
So to celebrate this news, we've decided to ask some of you to tell us all about your astronomy story. And seeing as we're here in the Midlands, we're starting with Stacey from Longbridge.
I first looked up at the night sky with real interest when the comet Hale-Bopp appeared. And I was about 7 or 8, I think, at the time. It did definitely light a fire in my brain that this was really cool. So it came to my late 20s, moved into this house, garden was relatively dark, and I just decided I needed a telescope in my life after all this time. And the rest is history, and my bank account is now significantly lighter. So my first astro image that I ever took, I honestly remember feeling like a crazy person. When it appeared on the back of the camera, I just was like, I ran around the house going, "Oh, I've got some galaxies!" And that was it, I was hooked. So, as my hobby has progressed, my partner Naomi, she has got irritated at the number of telescopes. I did have pretty much one in every room apart from the bathroom. But now the telescopes have been relocated up into my office, aka the telescope cave, and she's much happier now, and that means I'm happy. One of my favourite photos is of the Rosette Nebula. Use different filters to capture the different wavelengths of light, and you can have whatever colour palette you want, and I made it like pinky blue. I call it art meets science. I think doing astrophotography or astronomy, whatever your discipline that you're interested in, I think it's a great meditative process. I've almost described it to some people as like quiet time, but with focus. And just getting out under the sky and being in nature, that's something I really enjoy. I will never forget seeing the Milky Way for the first time, and I will never ever forget seeing those galaxies appear on the back of my camera. It puts perspective into life, because you think, I'm looking at this galaxy and it's however million light years away, and there's so many stars in it, and we're here on this tiny blue planet in the middle of our solar system. It is just, it's indescribable, really.
We're looking forward to meeting more of you in the coming months. But if you're looking for inspiration as to what to view in the night sky, here's Pete in his back garden with his telescope.
Now, if all this talk of exoplanets has made you want to go out and look for the planets in our own solar system, you might be a bit disappointed at the moment. And the reason for that is simply because most of them are now in the morning sky, so you have to get up very early. Because it's spring, the planets in the morning sky rising before the sun aren't optimally placed. They tend to be quite low down just before sunrise, and that makes them harder to see. Having said that, there is an event I want to draw your attention to, but I'll come back to that in a moment. In the evening sky, 2 planets remain. One of those is dim and distant Uranus. Now, this is never the brightest of the planets anyway. It's always on the threshold of naked eye visibility, and at the moment it's quite close to the sun, which makes it difficult to see. It's not really a viable target. The other planet is Mercury. Now, Mercury flits around the sun, so it appears in the morning sky and then back into the evening sky, back into the morning sky, etc. On the 29th of April, it will appear at a point called greatest eastern elongation, which means its furthest apparent distance from the sun. So Mercury should be quite well placed for viewing. Now, to find it, you need to go out, say, 20 to 30 minutes after the sun has set. Do make sure the sun is properly set for safety, though. Use binoculars and scan the region low above the west-northwest to northwest horizon. And if you find that tiny pinprick of light, that'll be Mercury. And if you stick with it, you've got a flat horizon in that direction, you may be able to make out the faint stars of the Pleiades open cluster just forcing their way through the evening twilight. Now, Mercury stays near the Pleiades for the next few evenings, and if you can remain with it, say through to the 2nd of May, then you'll be treated to a 3% lit waxing crescent moon really nearby as well. Now, I mentioned there was something else I wanted to bring your attention to in the morning sky, and this occurs on the morning of the 1st of May. If you get up early on this morning, say 30 to 40 minutes before the sun comes up, look low above the eastern horizon and you should be able to make out the brightest planet in the solar system. That's Venus. The next brightest is Jupiter, and Jupiter will be really close to Venus on that morning, and I mean really close. It'll be 22 arc minutes away from Venus, and that's about 2/3 the apparent diameter of the moon in the sky. So that's pretty close, and it's certainly worth setting your alarm early for.
Last summer, we talked to Johnny Nichols about his thoughts on the puzzle of what's causing Jupiter's astonishing aurora.
The idea is that the energy for Jupiter's auroras comes principally from the planet's rotation. Jupiter rotates very quickly, once every 10 hours or so, and that energy source drives Jupiter's auroras.
Since then, Johnny's been able to back up that idea with hard data. But it wasn't all plain sailing, as Maggie's been finding out.
John, it's lovely to see you again. Now, last time you were speaking, you were talking about sort of your theories of Jupiter's aurora, but initial data from Juno didn't seem to sort of match up with this. But that's changed. So what's happened?
So we've had theories about what drives Jupiter's auroras for about 2 decades now. But when Juno got to Jupiter and searched for signatures of the current system that is in this theory and the way it relates to the auroras, the two didn't quite match up. It was very confusing as to what was going on. And so the ideas that we had were thrown into question. But what we've done since then is we've used Juno data when Juno was out in the magnetic field. We measured the electric current at the same time as when the Hubble Space Telescope was looking at the auroras. And we found a very strong correlation between the intensity of the auroras and the magnitude of the current that's flowing in the system. In fact, over 80% of the variation in the auroral intensity can be explained by changes in the electric current system flowing. So that's really strong confirmation that our theories that we've had for the last couple of decades are actually correct.
So it was a combination of seeing the local, but also the far away at the same time that enabled you to do this correlation.
Yeah, that's right. We needed to be far out in the magnetic field so that Juno was able to measure the currents that are flowing. But when it's far out in the magnetic field, it can't observe the auroras. So we needed the Hubble Space Telescope to be able to take pictures of the auroras at the same time. And we compared the two. And when I saw the strength of the correlation, I nearly fell off my chair. It was amazing to see such a direct correlation between those two phenomena.
Fantastic. But it sounds as if that your job's almost done. I mean, you're getting good correlation now. Is this the end of the story?
This is not the end of the story. No, we really still need to be able to understand how the electrons are accelerated above Jupiter's auroras. We don't understand why we see what we see above Jupiter's, very close above Jupiter's auroral region. So it's not all done and dusted yet. Jupiter still does hold on to some of its secrets.
Oh, fantastic. Well, I look forward to speaking to you as more gets revealed. But thanks so much for talking to us again. Take care.
Thank you.
Well, it's always great to learn new things. And on that note, in March, we had the discovery of a whole new astronomical unit of measurement.
I think I must have missed that.
Well, it was the Daily Mail, and to be fair, lots of other people carried the story of an asteroid that was seen entering the Earth's atmosphere and landing in the North Sea, which is interesting enough. But the point was, they all described it as being the size of half a giraffe.
Half a giraffe. A calibrated giraffe. And also, which half? Are we talking about sort of, top to bottom, left to right?
Well, the Mail at least translated it as 10 feet, so I think that's top to bottom. I'm not sure about the calibration.
Yes, and about 3 metres.
But I quite like this idea. Yeah, 10 feet, 3 metres. This is good. We'll use these proper units. But half a giraffe to those in the know. But I like this future. I like the idea of, disaster announcement. There was an asteroid spotted on the way to the Earth. It is 200 giraffes across. Run for cover immediately.
Yes. Oh, no, 200? We'll never survive.
Way too many.
Yeah, I think it could cotton on. But speaking of meteorites, I mean, last year we were talking about the Winchcombe meteorite, which was tracked to its sort of landing location by the aptly named Fireball Alliance, which I love.
The Fireball Alliance tracked the Winchcombe meteorite with a network of cameras operated by members of the public. And since we featured that story, lots of you have got in touch with them, and the size of the network has nearly doubled, which is brilliant news.
Yeah, I think it is wonderful that people are getting involved in astronomy. And if you'd like to join the Alliance, then do look at our website where the details are there.
Next month, we'll be talking about the moon, a celestial object 0.6 megagiraffes across.
In the meantime, from here at the University of Birmingham, good night.